So how exactly do we render a million tiny details without actually using a million polygons? Let's dive right in. Have you ever stopped to wonder how modern graphics engines manage to show us hyper-realistic, intricate details like the rough bark of a tree or the porous, jagged surface of a rock without completely melting our GPUs? It's a massive computational challenge. If you try to render every single tiny detail with an actual physical geometric polygon, your hardware is going to grind you an absolute halt. So how do they actually pull it off? Well, you can really see the stark visual difference between the old way of doing things and the new. On one hand, you've got the jagged reality of older methods. You get those ugly, stair-stepping artifacts on the edges, which is exactly what happens when traditional 1D height maps try to fake geometry on a low polygon mesh. It just looks off, right? But then, contrast that with flawless 3D mapping. It looks exactly like a heavy, high-resolution model, but under the hood, it's remarkably lightweight.
Welcome to the Explainer. Today, we're going to solve this rendering mystery together. We're looking at curvature and cheats, the math behind 3D displacement mapping. We're going to break down the fascinating math, the clever algorithmic cheats, and the brilliant solutions that allow computer graphics to give us infinite detail without the infinite computational cost.
Here's our game plan for today. We'll start with the problem with polygons, move into 3D displacement mapping, and then walk through the 3 steps of the algorithm: finding curvature, smart parametrization, and map generation. Finally, we'll wrap up with how this all leads to flawless real-time rendering.
All right, Section 1. The problem with polygons, and exactly why flat shapes fail complex surfaces.
Okay, so to truly appreciate the solution here, we kind of need to remember why this has historically been such a massive headache for developers. And it all boils down to tessellation. Basically, tessellation is the process of taking a surface and dividing it up into a grid of much smaller polygons to increase the geometric detail. It's like taking a single square piece of paper and folding it into a grid of 100 tiny squares. If you want more detail in computer graphics, traditionally, you need a much higher degree of tessellation. But, as we know, high tessellation is incredibly expensive for a machine to process.
Now think about self-occluded objects, things like curling wood or overlapping rocky shapes. These are notoriously difficult to render using older methods. Traditional 1D displacement mapping just takes a flat surface and pushes pixels straight up vertically, based on a height map. But because it literally only pushes straight up, it is physically impossible to render complex surfaces that fold over themselves. The math just flat out doesn't allow for it.
Which brings us to Section 2. Enter 3D displacement mapping. We are literally bending the rules of geometry here.
This technique is absolutely the mathematical hero of our explainer. Let's compare the two side by side. Think of 1D displacement like pushing pins straight up from a flat corkboard. It only measures height, it demands a heavily tessellated surface to look even half decent, and it completely fails at self-occlusion. 3D displacement, on the other hand, it's like allowing those pins to twist, lean, and stretch in literally any direction. Because it uses 3D vectors instead of just height, it only needs a very low fixed level of tessellation, and it easily handles complex folded geometry. It is just vastly superior.
So how does this actually build into a software pipeline? Well, the 3D displacement algorithm consists of 3 strictly procedural stages. Step 1, vertex weight estimation. Step 2, parametrization. And Step 3, map generation. Let's break these down one by one.
Step 1. Finding curvature, or identifying the bends. Before the computer can render the details, it first has to figure out which parts of a 3D model are mathematically the most important to the human eye. If you look at standard 1D vertical displacement, it's just arrows pointing straight up. But with 3D vector displacement, you can actually see how the vectors map to the geometry. The arrows are angled. The computer is actively shifting points along complex angles instead of just moving them up and down, which is what allows the mesh to fold over itself and create really sharp edges.
And here is how the computer actively hunts for those important spots. Look at these surface curvature values. The system uses something called the curvature normal equation to find the parts of the model that bend the most. Wherever you see the lighter, brighter red colors, that represents areas of much higher curvature. Basically, the system is saying, this area is highly detailed and sharp, so we need to assign more mathematical weight to the vertices right here.
But of course, there's a catch. If you just use the raw curvature, you get visual glitches. Why? Because the exact same distance error in a 2D texture map can result in vastly different amounts of actual 3D geometric error when rendered out. To fix this, the algorithm uses a really clever approximation. It multiplies the mean curvature by a factor of 4a. Now, without getting bogged down in the deep calculus, this just ensures that larger physical distances on the model get adequate texture space, entirely preventing those ugly rendering errors.
Moving on to Step 2, Smart Parameterization, squishing and stretching the map. Once the algorithm knows exactly what parts are the most curved, it has to map those 3D shapes onto a flat 2D space. And this is so cool. You can literally see how the highly curved areas from our red curvature map perfectly match up with the dense squish clusters in the parameterization wireframe. The algorithm is dynamically squishing and stretching the triangles to give way more detail and vertex density to those highly curved areas, essentially stealing geometry from the flat, boring parts of the model where detail just isn't needed. Now, to actually do the stretching and squishing, the system uses an edge spring algorithm that literally pushes vertices apart based on their weight. But you have to be careful not to stretch things too far, or the final texture is going to look terrible. So the algorithm runs a continuous safety check using Heron's formula. It constantly compares the area of the ideal triangle with the area of the current triangle in the texture map. If it gets too distorted, it pulls it back closer to an equilateral triangle. It's just a remarkably elegant automated self-correction system.
Which takes us to Step 3, map generation, and creating the final instruction set.
So we have our weights, we have our squished layout, and now we need the final instruction set. This beautiful, strange-looking blue image you're seeing is the actual generated 3D displacement map. But what you are really looking at here is pure vector data. In this final step, a one-to-one mapping function calculates the displacement vectors in the tangent space of the coarse mesh. To the computer, these colors aren't colors at all. They are strict directional instructions telling that very low-resolution mesh exactly how to push and pull its geometry in 3D space to reconstruct the high-resolution original.
Finally, Section 6, Flawless Real-Time Rendering, the final result.
So what does this actually look like when we bring all of this crazy math together? Look at the full pipeline here. We start with a highly detailed input mesh, like a stone wall. Next, the algorithm calculates its curvature. Then, it uses that data for parameterization, squishing the wireframe. That data generates the 3D vector map. And finally, the graphics engine outputs a flawlessly reconstructed surface. But here's the absolute magic of it. That final reconstructed image is actually built on an extremely coarse, low polygon mesh. It saves massive amounts of computing power while looking totally identical to the original high-res model.
And the field of computer graphics is just evolving at lightning speed based on these exact foundational concepts. Today, we're seeing developers implement incredible advancements. We've got diag split, which allows for parallel, crack-free adaptive tessellation for micropolygon rendering. We are seeing the massive rise of completely virtualized geometry, like Unreal Engine's nanite system, working right alongside parallel Catmull-Clark subdivision and advanced supercompression techniques from companies like AMD. The math is getting faster, it's getting smarter, and it's infinitely more capable. Which leaves us with a truly fascinating question to end this explainer on. As software algorithms and mathematical cheats get this incredibly smart at faking infinite detail on low-resolution geometry, will hardware ever actually need to process infinite polygons? Or will the math just always outsmart the hardware limitations? It's this brilliant cat-and-mouse game between physics and code, and it's absolutely what makes the future of rendering so exciting. Thanks for joining me on this explainer. Keep questioning how the digital world is built.